this video, we're going to introduce polynomial functions and polynomial inequalities. So let's first define what we mean by a polynomial. So we've got this polynomial we're defining as a function p of x. Notice that the powers on the x, where they appear here, are to non-negative integer powers. So say this is maybe a 5, this could be a 4, this could be a 1. Here would be kind of an understood x to the 0. But notice that there are no fractions as exponents and there's no negatives as exponents. So whenever we see an exponent on an x, it has to be to a positive power, and we could add a constant at the end. These other a sub n, a sub n minus 1, and so on down the line, those are just numbers. Real numbers for the time being, but those are just numbers. So that's what we mean by a polynomial. All right, so when we have this first term here, or the term with the highest exponent on it, when that a sub n is not 0, so we mean we really do see this first term here, we say that the degree of the polynomial is n. So that's the highest power of x that we see in the polynomial. That's what we mean by degree. And then the coefficient on that highest degree term, that highest degree x term, is what we refer to as the leading coefficient of the polynomial. If we have all zeros for all the a's, so basically we have p of x equals 0, we call that the zero polynomial, and we do not define a degree in that case because we really can't tell if we have a 0 or a 0x or a 0x squared or so on. So the degree for the zero polynomial is undefined. So let's look at an example. If we have the function p of x equals 7x squared minus 6x to the 8th plus 4x minus 7 plus 2x cubed, we see that this really is a polynomial. We haven't written it in what looks like a standard form up here, right? Because our powers are not decreasing. But it's still a polynomial because, again, it fits all the characteristics that we want. When we see an x to a power, that power is a positive integer power. So looking at this polynomial, we see the highest degree, the highest power on x that we see is 8, so the degree is 8. The coefficient on that x to the 8th term is a minus 6, so the leading coefficient is negative 6. Like I just mentioned a minute ago, we usually write the terms so that the powers on the x decrease, so we would rearrange this as negative 6x to the 8th plus 2x cubed plus 7x squared plus 4x minus 7. All right. One of the things they're going to be interested in for polynomials is finding their zeros, or finding their roots. So we call a number c, which could be a complex number. It doesn't have to be a real number, but it could be complex. We call this a zero, or a root of the polynomial, if when we plug the number into the polynomial, we get 0 out. So corresponding that to a graph, if we have a 0 for the polynomial, then the point c comma 0 is an x-intercept of the graph, and that's where the name root comes from. We think about the polynomial being rooted on the x-axis at its roots, where it crosses the x-axis. In the previous example, that polynomial has a 0 of 1, because if I plug 1 into the polynomial, I get 0 out. Let's see if we want to do an example here of finding the zeros of f of x equals 2x cubed minus 3x squared plus x. So in order to find these zeros, we're going to factor. So we'll set the equation equal to 0, or set the function equal to 0. We notice that we have a common factor of x in all three terms, so we factor that out. We now factor the trinomial that we have. That 2x squared minus 3x plus 1 factors as 2x minus 1 and x minus 1. And then setting each factor equal to 0, we see that the polynomial has zeros of 0, 1/2, and 1. And if we look at the graph of this polynomial, we do see the polynomial crosses the x-axis at 0, at 1, 0, at 1/2, and at 1. So we can use these intercepts and something else referred to as end behavior to help us sketch a rough graph of polynomials. So when x goes to positive or negative infinity, it turns out that the highest degree term is the one that determines what happens with the graph. And so we refer to this typically as the tails of the graph. So it's the highest degree term that dominates the tails of the graph. So if we have a sub n times x to the n as the highest degree term, or the leading term of the polynomial, then we can summarize the end behavior as follows. So if n is even and the leading coefficient is greater than 0, then, well, I don't really know what happens in the middle. There's lots of different things that could happen in the middle, but I do know that on the tails, both tails should point upward, looking like, say, y equals x squared, if you will. So we write this, I know it's a little hard to see because it's a little small, but we write this as x goes to infinity, f of x goes to infinity, and as x goes to minus infinity, f of x also goes to infinity. So we use this arrow notation to describe end behavior. So all this says is that as x gets large in the positive direction, f of x also gets large in the positive direction. So that's describing this right tail. As x gets large in the negative direction, f of x still gets large in the positive direction. That's describing this left tail. But what happens if n is odd? Well, then we get this one where the left tail is pointing down and the right tail is pointing up, looking a lot like x cubed. So here would be the description of that end behavior. As x goes to infinity, f of x goes to infinity. And as x goes to minus infinity, f of x goes to minus infinity. Now to see what happens when the leading coefficient is negative, well, we already know that if we multiply on the outside by a negative, it flips it across the x-axis. So basically it's the same type of picture that we have above, just flipped upside down. So both tails will be pointing down in this case if n is even. And if n is odd, then the left tail will point up and the right tail will point down. And you can also see the descriptions of the end behavior here. So let's go back to the example we did before, the f of x equals 2x cubed minus 3x squared plus x. Find the x-intercepts, find the y-intercept, and find the end behavior, and then use this information to sketch a graph. So we already saw that the zeros are 0, 1/2, and 1. So that means that our x-intercepts are the points 0, 0, 1/2, 0, and 1, 0. To find the y-intercept, we plug in 0 for x and figure out what the y value is. In this case, we also get 0 out for the y, so the y-intercept is the same as the x-intercept, 0, 0. Let's look at the end behavior now. The highest degree term is 2x cubed, so the degree is odd and the leading coefficient is positive. That tells us that the right tail points up and the left tail points down. So we describe that in symbols as x goes to positive infinity, f of x goes to positive infinity. And as x goes to minus infinity, f of x goes to minus infinity. So again, saying it in words, as x gets large in the positive direction, f of x gets large in the positive direction. So that's telling us our tail is pointing up and to the right. And this says that as x gets large in the negative direction, f of x gets large in the negative direction, or the tail is pointing down to the left. And this looks like the same graph we did before, which it should, and we see that end behavior here. We've got this tail going up to the right, this tail going to the left, and then we've got these other intercepts. Let's do another example, a little bit more complicated. This one to give us a polynomial in factored form. We have g of x as negative 3 times x plus 4 times x minus 1 times x minus 2 times x minus 5. We're asked to find the degree, the leading coefficient, the x-intercept, the y-intercept, the end behavior. Lots of information. But now we should have a good information to be able to sketch a graph of this function. All right. Let's not actually multiply out the polynomial, but if we were, we would see that we have to do an x times an x times an x times an x. That would give us an x to the 4th. That's the highest power of x that we could get. So that tells us the degree has to be 4. To get that x to the 4th, we really do have to multiply those 4 x's together. That would also get multiplied by the negative 3. So the negative 3 would be the leading coefficient. All right. So if we want to find the zeros, we would set the function equal to 0. Since it's already factored, it's pretty easy to read off the zeros. This one gives us a 0 of -4. This factor gives us a 0 of 1. This factor gives us a 0 of 2. And this factor gives us a 0 of 5. So the x-intercepts are -4, 0, 1, 0, 2, 0, and 5, 0. To find the y-intercept, we replace x with 0 and compute g of 0. In that case, we get 120. So our y-intercept is the point 0, 120. Finally, going back to our degree and our leading coefficient, the degree is even. Even-degreed polynomials have the tails pointing in the same direction. Either both are up or both are down. And since the leading coefficient is negative, both is down. Both tails will be down. So as x gets large in the positive direction, as x goes to positive infinity, f of x goes to minus infinity. Again, this is referring to the right tail. This is the right tail points downward. As x goes to negative infinity, f of x still goes to negative infinity. This is the left tail goes down. Here's a rough graph. It's not a great graph of the polynomial, but it's a rough graph. Putting in the zeros, -4, 1, 2, and 5. Putting in the y-intercept of 120. And we know that it points down, the tails point downward. So we start from lower left, go through the 0, go up through the intercept, down through the 0, back through the 0, down through the 0, and then the right tail pointing to the lower right. Last thing we're going to talk about here is how to solve a polynomial inequality. So let's say we have the polynomial x plus 5 times x minus 3 squared times x minus 7. We want to know when that is above the x-axis or on the x-axis, greater than or equal to 0. Well, to figure out what we're going to do, we're going to look at first where the polynomial crosses the x-axis. Well, that's not too hard to find because it's already factored for us. We get zeros of -5, 3, and 7. And that's the only places where this function can cross the x-axis. If there's another place it crossed the x-axis, we would have found it. So what that tells us is that whatever is going on for the function in between these 2 points, it has to be the same throughout that entire interval. And what I mean is, if it's above the x-axis at a point between -5 and 3, it still has to be above the x-axis anywhere between -5 and 3. So what this tells us that we can do is we can use these points to divide the x-axis into intervals and then check whether the graph is above or below the x-axis at some point on those intervals. So let's make a table. We have the interval from -infinity to -5, because that's the lowest 0 that we have. -5 to 3, 3 to 7, and 7 to infinity. So these 3 points divide the x-axis into 4 intervals. Now we get to choose test points. Doesn't matter what they are as long as they're in the interval. So I'll choose -6, 0, 4, and 8. Those satisfy that. And now all we care about is what the sign of f of x is, whether it's positive or whether it's negative. So if we go back to the original and put in -6, well, this term will be negative. This term will be positive no matter what we plug in. This term will also be negative. So we get negative times negative makes positive. So the function is positive at -6, so it's positive at all points in this interval. Put in 0, we get positive times negative. And we can see that with the actual numbers that are plugged in here. So it'll be negative. So again, that tells us that on the entire interval from -5 to 3, the function is negative. Put in 4, we'll get a positive times negative. So the whole thing is negative. Finally, to plug in 8, we'll get positive times positive, so the whole thing is positive. We're looking for the solution for the function to be greater than or equal to 0. So we're looking for the positives. Well, we're going back up to our table. It's positive on the interval from -infinity to -5, and it's positive on the interval from 7 to infinity. So we want to choose those 2 intervals, and then we actually include the endpoints in this case because we want greater than or equal to 0, not just greater than 0.